And welcome back. As we continue our cosmic journey, let's go ahead and continue looking at the moon by going ahead and examining the lunar surface. So when we start talking about the lunar surface, let's first look at the general appearance of that surface. If you look at the moon through a telescope, you can see that it's covered by impact craters of all sizes. The most conspicuous of the moon's surface features are vast splotches of darker lava flows. Centuries ago, early lunar observers thought that the moon had continents and oceans, and that it was possible abode of life. They therefore call these dark areas seas, which we refer to as Maria. The names Mare Nubium, which is the Sea of Clouds, Mare Tranquillitatis, which is the Sea of Tranquility, and so on are still in use today. In contrast, the land areas between the seas are not named. Thousands of individual craters have been named, however, mostly though for great scientists and philosophers. So what are the similarities in the surface of the moon with what we already know about our own planet? Well, we know today that the resemblance of lunar features to that of the terrestrial ones on Earth is superficial at best. Even when they look somewhat similar, the origins of lunar features, such as craters and mountains, are very different from their terrestrial counterparts. The moon's relative lack of internal activity, together with the absence of air and water, make its geological history unlike anything we know on Earth. Remember, for example, on Earth, mountain ranges are subject to erosion from wind, water, and rain, and so these things can really shape and sharpen the surfaces that we know. If you look at this picture here, you can already see that these mountain surfaces are very different from what we might encounter. So, to understand this, we need a little bit of lunar history. To trace the detailed history of the moon, or really any planet, we must be able to estimate the ages of individual rocks. Once lunar samples were brought back by the Apollo astronauts, the radioactive dating techniques that we had developed on Earth were applied to them. The solidification ages of the samples ranged from about 3.3 to 4.4 billion years old, which is substantially older than most of the rocks on Earth. If you recall, both the Earth and Moon probably formed about 4.5 to 4.6 billion years ago. And so when we start looking at some of this composition, let's first look at the lunar highlands. Most of the crust of the moon, which is 83%, consists of silicate rocks known as anthracites in regions known as the lunar highlands. These are made of relatively low density rock that's solidified on the cooling moon like slag floating on the top of a smelter. Because they formed so early in lunar history, between 4.1 and 4.4 billion years ago, the highlands are also extremely heavily cratered, bearing the scars of all those billions of years of impacts by interplanetary debris. Now, there are, of course, lunar mountains, as I already mentioned. Unlike the mountains of Earth, the moon's highlands do not have any sharp folds in their ranges. You can look right here at this mountain, and it looks relatively smooth. The highlands have low, rounded profiles that resemble the oldest, most eroded mountains on Earth. And because there is no atmosphere, or water on the moon, there's been no erosion to carve them into either cliffs or sharp peaks, which is, of course, the way that we would picture our moon's mountains had they been here on Earth. These smooth features are attributed to, instead, gradual erosion, which is mostly due to impact cratering, because when impact happens, it still throws up stuff into the moon's non-existent atmosphere that still eventually comes down and pelts these surfaces to smooth them out. Now let's talk about the other feature of the moon, which is that of Maria. The Maria are much less cratered than the highlands and cover just about 17% of the lunar surface, which is mostly on the side of the moon that faces Earth. This view of Imbarium also shows numerous secondary craters and evidence of material ejected from the large crater Copernicus on the upper horizon. Copernicus is an impact crater almost 100 kilometers in diameter that was formed long after the lava in Imbarium was already deposited. And so if we start looking at some of these lunar rocks, we can actually get a better picture of some of the moon's history. The Maria consists mostly of dark colored basalt volcanic lava laid down in volcanic eruptions billions of years ago. Eventually, these lava flows partly filled the huge depressions, which we call impact basins, which are produced by the collisions of large chunks of material with the moon relatively early in history. Now, the basalt on the moon is very similar composition to the crust under the oceans of Earth, or to the lavas erupted by many of our terrestrial volcanoes. So, if we have volcanoes on the moon, what kind of volcanic activity could we expect, or did we expect, since the moon seems to be no longer geologically active? Volcanic activity may have begun very early in the moon's history, although most evidence of the first half of a billion years is pretty much lost. What we do know is that the major volcanism, which involved the release of lava from hundreds of kilometers below the surface, ended about 3.3 billion years ago. After that, the moon's interior cooled, and volcanic activity was limited to a few small areas. The primary forces altering the surface come from the outside of the moon, not the inside. And so, let's go ahead and wind this back to the lunar surface itself. The surface of the moon is buried under a fine-grained soil, tiny shattered rock fragments. The dark ballistic dust of the lunar area was kicked up by every astronaut's footstep when they went and explored it, and thus eventually worked its way into all the astronauts' equipment. The upper layers of the surface of the moon are very porous, consisting of loosely packed dust into which their boots sank several centimeters. So it was, like walking on a powder. This lunar dust, like so much else on the moon, is the product of all the impacts that the moon has suffered over the years. Each cratering event, whether it's large or small, breaks up the rock of the lunar surface and scatters the fragments. Ultimately, billions of years of impacts have reduced much of the surface layer to particles about the size of dust or to sand. In the absence of any air, the lunar surface experiences much greater temperature extremes than the surface of Earth, even though Earth is virtually the same distance from the Sun. Near local noon, when the Sun is high in the sky, the temperature of the dark lunar soil rises above the boiling point of water. And then, during the long lunar night, the temperature drops to about 100 Kelvin, or minus 173 degrees Celsius. The extreme cooling is a result of not only the absence of air, but also the porous nature of the moon's dusty soil, which cools much more rapidly than solid rock would.